Welcome back to this series on topology. In today's video, I'll be talking about countability properties, which describe how large a topology on a space is. You can find a playlist that contains all the videos in this series by clicking on the info thing that should appear right now. In the last video, we talked about what it means for a collection of open sets to be a basis for a topology. And today we'll be using this notion of a basis in order to bound the size of a topology on some space. If we're given some topological space, then we call it second countable if it has a countable basis for its topology. Now in general, a topological space with a given topology can have many bases, and these could also have varying sizes, so some of them could be uncountable and some of them could be countable. But we'll just call the topological space second countable if at least one of its bases is countable. The prototypical example for a second countable space is just Euclidean space. Now, according to the definition, in order to show that Euclidean space is second countable, we have to come up with a basis for it which is countable. Remember from the last video that we saw a basis for Euclidean space, namely the set of all open balls at every point in the space. So let's look at Rn, Euclidean space of dimension n, and now a basis for Rn, which I'll denote B, was given by the set of all open balls of radius r at the point, let's say P, for which R is a positive real number and P lies within Rn. We saw last time that this collection curly B forms a basis for the topology on Euclidean space, which means that every element in the collection is an open set of Euclidean space Rn, and also that any arbitrary open set in Rn can be written as the union of basis elements. However, this basis, curly B, is not countable. To see why this is the case, we can just fix some point P in Rn. Well, then the collection, which I'll call BP, which is the set of all open balls at this fixed P, this is uncountable because the positive real numbers are uncountable. In fact, the cardinalities of this collection BP and the positive real numbers coincide because for each radius in the positive reals, we have some element in the collection, and conversely, if we take some open ball around P in the collection BP, it'll have a radius which lies in the positive reals, and these two maps are inverse to one another. Now it just remains to note that this BP is a subset of B, and so this means that because BP is uncountable, also its superset, curly B, needs to be uncountable. So in summary, we've seen that the standard choice for a basis of Euclidean space doesn't show that it's second countable. However, there's a way that we can modify this basis in order to make it countable while still retaining the basis property. And I'll show how this works right now. The idea behind what we're going to do is we're going to use the fact that the rational numbers, which are countable, form a dense subset of the real numbers. Thus, everywhere where we have the reals appearing in this basis, we're going to replace them by the rational numbers. This will give us a new collection, which I'll call C, which are, again, going to be open balls of radius r at points P. However, now the radius is going to lie within the positive rational numbers, and our point P will lie within Q to the n. In fact, this substitution does the trick for the countability. So if we again fix some point P in Qn, well, then the set, which I'll call Cp, so these are all the open balls of radius r at P, where r lies within the positive rationals. So this set is countable. This is because this set Cp has the same cardinality as the positive rationals, because we have one open ball for each radius in the positive rationals. And moreover, the collection C is just the union over all points P in Qn over the collections Cp. Now, because Q is countable, also its n-fold Cartesian product, Qn, is countable, which means that what we have here is a countable union over countable sets, and this is in turn again going to be a countable set. Hence our collection C is countable as we claimed above. So far so good. We've managed to restrict this uncountable collection B to a collection C which is countable. However, we still have to check that this restricted collection is still a basis for the topology on Euclidean space. So remember from last time that in order to be a basis, a collection has to satisfy two properties. First of all, every element of the basis has to be an open set in the topology we're interested in. And second, we have to be able to write every arbitrary open set of the topology in terms of a union over basis elements. Now, because we've simply restricted our collection B, it means that every element in C is still going to be an open set of Euclidean space. So these open balls with rational radii at rational coordinates, these are still just open sets in Euclidean space. So the first condition really follows easily from the fact that we've just restricted our larger basis curly B. To show the second property, let's consider an open subset U of Rn and some point x in U. Now, by the definition of what it means to be an open subset of Euclidean space, there exists some radius which is a positive real number, such that the open ball of radius r around x is contained within U. Now, by basic properties of rational and real numbers, there is some q in the positive rationals with q less than or equal to this radius r. This is a consequence, for example, of the Archimedean property of the natural numbers. So think about the number 1 over r. Because the natural numbers are unbounded, there's going to be some natural number n which is greater than 1 over r, which means in turn that 1 over n, which is a rational number, is going to be less than or equal to r. Moreover, by the denseness of the rational numbers within the reals, there's going to be some rational point P in Qn such that the distance between x and P is going to be strictly less than Q halves. Remember that Qn being dense in Rn means that the closure of Qn is equal to Rn. And one way of characterizing the closure is saying that a point is in the closure if and only if every open neighborhood around that point intersects the set that is being taken the closure of. So in our case, we have this point x, which is in the closure of Qn, and so we can take the open ball of radius Q halves. This is an open neighborhood around x, so this open ball will intersect Qn, meaning that there exists some point P in Qn that lies within the open ball, which is just this condition here that the distance between x and P is strictly less than Q halves. So in summary, we've started with some arbitrary point x in U, which can have real coordinates, and we found an open ball of radius r around that point, which lies within U, and this radius r is also a positive real value. And now we found a rational radius q, which is less than or equal to this radius r, and also some point P with rational coordinates that has distance from x strictly less than Q halves. Hence x lies within the open ball of radius Q halves around P, and this is in fact a subset of the open ball of radius r around the point x, which lies within U. So the fact that x lies within this open ball of radius Q halves around P follows just from this condition here. Next, suppose that we have some point y lying within this open ball of radius Q halves around P. Well, in that case, y will have a distance from P strictly less than Q halves, but we also know that P has a distance from x strictly less than Q halves. Now, by the triangle inequality, the distance between y and x will be less than or equal to the distance between y and P plus the distance between P and x. And we know that both of these distances here are strictly less than Q halves. So this entire sum is going to be strictly less than Q, and we know that Q is less than or equal to R, which means that the distance between y and x is going to be strictly less than R, meaning that this y also lies within the open ball of radius r around x. And finally, the last inclusion follows from our assumption here that the open ball of radius r around x lies within U. Okay, so we've had to mess around a bit with converting these points with real coordinates into rational coordinates and converting radii of real values into rational values, and then coming up with a suitable way to adjust these radii in order to get this last condition, which is really what we want. So in summary, given an arbitrary point in U with real coordinates, we can find a open ball. So this is this B of radius Q halves at P. We can find an open ball with rational radius and at a rational coordinate that lies completely within U. And this fact will be sufficient to prove that U is actually equal to a union over elements out of the collection C. To reiterate what we've done so far, given an open subset U of Rn and some point x in U, there is what I'm going to be calling Cx in C, and we know from before that this is just this BQ halves at P, such that x lies within Cx, and Cx is a subset of U. And now we're almost done because we can just consider the union over all points P in our subset U, and we union over these sets Cp. And each of these sets Cp lies within the collection C. We now use this argument that we've already seen many times. In particular, we saw it last time in under the guise of the basis criterion. Namely, we claim that this union is actually equal U. So one inclusion, namely this left to right inclusion, follows from the fact that each of these sets CP is contained within U. Conversely, the other inclusion follows from the fact that we're unioning over each point in U and each point P is contained within CP. Okay, so we've shown that we can write U as a union over these CPs, and each of these CPs lies within C. Hence, we've written U as a union over basis elements of this collection C. This proves the second property we need for a basis, so indeed, this collection C is a basis. So in summary, we can restrict this standard basis curly B to the collection curly C, where we only look at open balls which have rational radii and which lie at points with rational coordinates. And this collection curly C will still be a basis because the rationals lie dense within the reals. Moreover, this collection curly C is a countable collection, which shows that Euclidean space is second countable by the definition of second countability. Now we know that Euclidean space is pretty special, and in fact, second countability is a pretty strong property. And you may have wondered why this is called second countability. This implies that there might be something called first countability, and in fact there is, and this is what we'll look at next. In order to define first countability, we'll need to first introduce the notion of a neighborhood basis. For this, we let X be some topological space and P be a point that lies within X. And now a collection, BP, of neighborhoods of P is called a neighborhood basis for X at P if every neighborhood of P contains some element B of BP. In other words, you can think of a neighborhood basis as just being a collection of neighborhoods at a point, such that an arbitrary neighborhood at that point contains one of the elements of that collection. We can now go on to define what it means to be first countable. So we say that a space X is first countable if it has a countable neighborhood basis for every point. Notice that this is a weaker property than being second countable, because a first countable space could fail to have a countable basis. However, the converse does hold, and in fact, every second countable space is in particular first countable. To see why this is the case, let's take some P in X, which is a second countable space. And now we consider the collection BP, which is going to be a subset of a countable basis B, and this BP is going to be defined to be the set of all basis elements in our countable basis B, such that P lies within the basis element B. So essentially we're just restricting our basis to those elements that contain the point P. Now, because BP is a subset of the countable collection B, it itself is countable. And moreover, I claim that BP is a neighborhood basis for X at the point P. Why is this? Well, let N be some neighborhood of P. In other words, N is an open set that contains the point P. And now we know by the basis criterion that for any point in an open set, there's going to be a basis element that contains the point and is contained within the open set. So in particular, for the point P, there's going to exist some element B in our basis, curly B, such that P is contained within B, and also B is contained within N. But now because P is contained within this B, it means that also this element B is going to be in our collection BP. And so we found an element in BP that is contained within the neighborhood N, and this shows that BP is a neighborhood basis. Finally, BP is countable because our entire basis B is countable. This means that we found for any point a countable neighborhood basis at that point. And this is, in fact, just the definition of what it means to be first countable. So in summary, every second countable space is also first countable. All right, so I've introduced these two countability properties, namely being first countable, which means that we have countable neighborhood bases at every point in our space, and also being second countable, which means that there is a basis for our topology that is itself countable. Now at the moment it might seem a bit mysterious why we care about these countability properties. Now second countability will be one of the defining features of what it means to be a topological manifold. On the other hand, first countability is a sufficient criterion in order for the topology on a space to interact nicely with convergent sequences. So you may know from some real analysis course that open and closed sets in Euclidean space can be characterized by convergent sequences. And in fact, this is the case for any first countable topological space. And this is what we'll look at next. The following proposition outlines some of these properties, and I hope it motivates why we would care about spaces being first countable, or also second countable because second countability implies first countability. So suppose for this that X is some first countable topological space, and that A is a subset of X, and P is some point in X. Then the following equivalences hold. First, a point P lies within the closure of A if and only if P is a limit of a sequence that lies within A. Second, P lies within the interior of A if and only if every sequence in the space X that converges to P lies eventually within A. In fact, A and B can be used to characterize open and closed sets. So we further have that a subset A is closed if and only if A contains every limit of every convergent sequence in the subset A. And finally, A is open if every sequence in X that converges to a point of A lies eventually within A. So you can think of these parts A and B of the proposition as being these local versions that relate to a point and sequences converging to that point. And then there's global versions which say that A is closed or open if you look at all of the sequences converging to any point in A and so on. Now I won't be proving this proposition, however I'll give some hints at why it's true. Let's start with point A. Now the first thing one needs to do is to observe that if one has a neighborhood basis at P, then one can assume that the elements of the neighborhood basis are nested. So this means that the elements of the neighborhood basis lie within a chain of inclusions. So if we have our point P, then here we have our element, let's say maybe B1, and then B2 lies within B1, and B3 lies within B2, and so on. So all of the elements of this neighborhood basis can be assumed to be nested. If one starts with an arbitrary neighborhood basis at the point P, one can obtain such a nested neighborhood basis by intersecting elements of the original neighborhood basis. In any case, because X is first countable and P lies within X, we'll have a neighborhood basis around P which is countable, And also, this will give rise to a nested neighborhood basis, which is countable. Moreover, if P lies within the closure of A, so this is this hypothesis here, then this means by the characterization of lying within the closure that each neighborhood of P will intersect A. So in particular, each of these elements Bi of the nested neighborhood basis around P will contain some point of A. And now we just set our sequence to be these points which lie in the intersection of each of the elements of our nested neighborhood basis with A. This will give a sequence in A, and moreover, this sequence will converge to P because given some arbitrary neighborhood n of P, by the neighborhood basis property, this will contain one of the basis elements. Let's say this contains, Bn. And now because these neighborhood basis elements are nested, every Bm for m greater n is contained within Bn, which means that all the elements of our induced sequence will also be contained within Bn, which is contained within the set n, and this means that the sequence lies eventually completely within the neighborhood n. This shows that the sequence that we got by intersecting each of these neighborhood basis elements Bi with the set A converges to the point P. So that's one direction of implication. Conversely, if P is the limit of a sequence of points in A, then we just choose some arbitrary neighborhood n around P, and then eventually the sequence, which are points in A, will completely lie within n, but this means that n intersection with A is non-empty, and because this holds for any neighborhood n of P, this shows that P will be in the closure of A. Okay, so that was a sketch of part A of the proof, and I'll leave it to you to think about part B, which again uses these neighborhood bases around the point P. Just as a reminder, one characterization of a point P being in the interior of the set A is that there exists some neighborhood of P that lies completely within A. Finally, I'll hint at why the point A of this proposition implies point C. This follows from the fact that one characterization of being a closed set is that if a set is closed, then its closure is equal to the original set and vice versa. So we can say that A is closed if and only if A is equal to its closure. Okay, so now suppose that A is closed. Well, we know that this means that A is equal to its closure. And now consider some convergent sequence in A. Now this convergent sequence will converge to its limit P, which is the limit of a sequence in A. And by part A of the proposition, this means that P lies in the closure of A, which is just A. So this means that A contains every limit of every convergent sequence in A. So we've shown this left to right direction. And conversely, assume that A contains every limit of every convergent sequence in A. Now assume that we have some point P in the closure. So we're in this situation here. Well, then we know that P is such a limit of a sequence in A, and by assumption, this P is contained within A. So in fact, the closure of A is contained within A, which means that the closure of A is equal to A because A is always contained within the closure of A, and by this equivalence, this means that A is closed, showing the other direction. So that was a brief sketch of why this part C of the proposition holds, and part D is analogous in the sense that it uses part B of the proposition in order to show this equivalence. And here for part D, we use the fact that A is open if and only if A is equal to the interior of A. So I encourage you to think through why these other parts of the proposition that I haven't discussed are true, and maybe even write out a detailed proof for each one of them. But in any case, I hope that at least this proposition shows why first countability is a useful property for the space to have. In essence, this proposition is saying that the topology on the space X, namely whether sets are open and closed, can be characterized in terms of convergent sequences on the space. Okay, so that's all I have to say about countability properties. We'll be seeing second countability again next time when we look at the definition of topological manifolds.